Okay, so today is conceptually one of the hardest. It's not a long lecture today. Okay, this is not long. Let's take 45 minutes, something like that. But conceptually, this one's hard. And the reason this one is hard is because you have to think backwards. It's hard enough thinking statistically, generally, probabilistically. It's even harder when you have to worry about the world working in an entirely opposite way than how it works. Also, me together words put not good. So, we care a lot about type 1 error. We've talked about that. We set the alpha level, right? We set that. The probability of a false positive, we set that. We make it 0.05, typically. Our software, so something like SPSS or PSPP, maybe you use, there's all kinds of other things out there. You can use R. There's a really nice one called JASP, J-A-S-P, which stands for Just Another Stats Package. If you don't want to look at that, it's cross-platform. It's really good, too. It's very powerful. I might start teaching using that. It just isn't an industry standard like SPSS or R. But when we do a t-test, for example, it'll give us an exact p-value, right? That's a thing. Why is type 1 error then more important than type 2 error? I guess is a question one could ask. It's a good question. Because type 2 errors, that's a false negative, are also bad. Right? False negatives are bad. False is bad. And we're supposed to do true. The idea is to find things that are there. So, historically, part of this is Fisher's fault. The null hypothesis that we know of, the thing that says there is no effect of the independent variable, that's a straw man, isn't it? Right? It's a straw man hypothesis. It's something we're setting up the hypothesis to destroy it. Right? You don't argue with somebody and they set up a straw man, you know that expression? Right? So, that's a thing. It's sort of disingenuous. None of us really think there's no effect. We wouldn't do the experiment if we thought there was no effect, would we? Would you design an experiment hoping to find nothing? Of course not. So you're setting up what is basically a straw man hypothesis. That's what you're doing when you do. Fisher didn't think so. Fisher thought there really was an important possibility that nothing happened. And Fisher did invent analysis of variance, so we got to give him some credit. On the other hand, it's a straw man. So he thought it was really an important possibility that nothing happened. So that's one thing. I guess this is kind of circular, but I say it's easier because our methods are set up that way. But then I said, why are our methods set up that way? Because I'm being circular. But it really is the case that we think about type 1 error all the time. When you were, first time you were taught in an intro stat course of any sort, about type 1 error, you were told about the probability of a false positive, right? It may have been taught to you, I taught it like a pregnancy test, and someone probably taught it to you originally as the innocent person going guilty, being found guilty in a court of law, right? And that's really powerful. That's a powerful thing. That's scary. So, we even teach it that way. We teach it like it's like an innocent person going to jail. Well, that's really pretty scary. Because usually these things aren't life and death. It's probably easier logically to set up an idea where literally nothing happened. So that's probably part of it. It's easy for me logically to say, this has no effect, rather than saying, this has an effect and I know what it is. Right? Because I don't know what the effect is, I'm looking to find it. So I don't know what it is. That's pretty different than saying nothing happened. Right? Saying there's no Santa Claus, spoiler alert, guys, no Santa Claus. Saying there's no Santa Claus is easy. Telling you there is a Santa Claus and which culture's Santa Claus is it, that's harder. Right? Where is the magical being? who brings Christmas presents on the 24th, or the 6th, or the 25th, or maybe it's New Year's Eve. People are great. So for HA, we have to also know how big the effect is. So if I say there's an effect of alcohol and memory, which there is, spoiler alert, there is on that too. Don't make that your honors thesis. That's done. How big? If I say none, that's easy. There isn't one. If I say there's an effect, you have to actually tell me how big the effect is, or you're not telling me the answer. That's almost. I can't think of an easy situation where that's going to work out, right? Okay, you all with me so far? We're good, yes? Okay. Now, the best of all possible worlds, we would minimize alpha and beta, that's the probability of type 1 error and type 2 error, and we'd therefore have the most power. Power is the probability of rejecting a false null, or it's 1 minus beta. So power is the probability of rejecting HO given HA is true, that's just probability notation. Okay? So probability of rejecting HO given HA is true. Those among you who have been paying attention, which I'm assuming is all of you, so far in the course will realize that when I talk about HA being true, that's, remember the chart that HO is true, HA is true, and then reject HO, do not reject HO. And I said, we never know reality. But, I have to know this. To figure this out, I have to actually know reality. I have to already know how the universe works to figure this out. I can't know this. So there's a problem. So we're going to have to make a lot of guesses. They're going to be educated guesses. They're going to be nice estimates. But they're guesses. Now we do that in stats all the time. This is going to be a lot fuzzier than you're used to. Okay, you're used to precision. You're used to reject HO, do not reject HO, critical value. We exceeded it. We don't exceed it. That's what you're used to, right? This isn't going to be like that. This is going to be like, it's kind of like this, and sort of like that, and also you have to know how the universe works. It's going to be a lot of here. Okay. A lot of things that will make you wonder, and if you do, please ask. Okay. So this is a scan from our textbook, the wonderful Howell textbook. So we have two distributions here. This is always what these pictures look like, and they're always hard to understand until you understand it, and then you complete sense. Like okay? So don't feel bad if you understand it. I will try to explain it 1,000 times. Well, we don't have that kind of time, but I'll explain it as best I can. Okay, we assume HO is true, right? That's how we start. We assume HO is true, and then we have a cutoff saying if it's really unlikely, that's the alpha level here. If it's really unlikely, we will then reject HO and say it is not true. Right? Ignore the other distribution for a moment, which is hard to do because it's looking at you. But ignore it. Do you understand that so far? That's good. Is it? Okay. So if it were the case that HO is true and we reject HO, there's a very small probability, and it's in the shaded region where you have an alpha pointing to it. Okay? Just right there. Okay. Now, because alpha is the probability of rejecting the null hypothesis when the null hypothesis is true. Okay. What if the alternative hypothesis, or H1 as it's called here, it's not called here, it's called H1. What if H1 is true? Now we have to ignore this distribution, the HO distribution. H1 is true. What's the probability of us not rejecting HO? Well, it's going to be everything to the left of this, right in this region that's called beta. Okay? Right there. because now H1 is true, but we have failed to reject it. It's a false negative. Now, what's the probability of rejecting a false null? In other words, the probability of rejecting HO if HA is true. Well, HA is true, and it's to the right of this, so that's all this unshaded area that's called power, or it's 1 minus beta. Okay. I want to see if you understand this. Are you okay with this so far? Okay. Because I know you've probably seen a picture like this before in stats class. Is that over? So, how would we increase the power? Now, you got to take a little bit of a flight of fancy here, because, which is a term I very rarely use, because it sounds weird. But you have to imagine you could do anything. Okay. How would you increase the power? In other words, we want to make this non-shaded white area underneath H1 bigger. How do we make that bigger? What could you do? Anybody? Imagine you could do anything, by the way. So you're thinking, oh, I can't do that tree again. Well, why don't we just make the difference between the distributions wider? Let's move one over. I think you can't do that. I said you could do anything. I have the utmost confidence in your ability. You can do anything. So yeah, we can make them further apart. We can make alpha bigger. What if we just pulled alpha all the way over here? You can't do that. Nobody's going to let you. But you could. It would increase your power. It would also increase your type 1 error rate. Okay, so that's the first. You can do that. You can do what I just said. Increase mu1 minus. You can't do that. Can you practically? I'm saying, imagine doing it. You can do whatever you want, but then I'm going to say you can't practically do it. Can you practically make alpha bigger? No, right? Because if you make alpha bigger, you make the probability of type 1 error bigger. It's not going to work. You do it sometimes. We talk about public health issues. It's often done with an alpha of like 0.15, which is fine by me. I don't want to get giardia. I don't want to get lung cancer from secondhand smoke. 0.15 is fine with me. Right? I don't want to get that crazy virus from Wuhan. That's going on, and I'm watching a documentary on Netflix last night about pandemics. And it's like, well, that's it. It's all over. It doesn't just fire up the division in practice, because that's coming. By the way, that show about the pandemic, it's in 4K. So I'm watching people be really, really sick, and it's hyper-realistic. So it's disturbing. We can't do this. We can't make mu1 bigger than mu0 because we can't move distributions. That's not a thing we can do. You can do that. People line up on a holy day and worship. You can't do that. That's not a thing you can do. What if we made... If we split, we're not going to move H1 or HO. We're not going to make alpha. What if we just suck these distributions in, make it smaller, make the sigma smaller? And you're saying, Dave, we can't change parameters. You're right. We can change. We don't deal with actual populations when we do statistics, do we? We deal with sampling distributions. Oh, this is why he tells us about the central limit theory. So we can actually it's going to decrease the overlap, and we're going to do it by decreasing the spread of both distributions. And again, I can't really decrease sigma, but I can decrease the standard deviation of the sampling distribution. Which I don't know what that points for. It's obviously nothing. So making the variance smaller will actually tighten up the distribution. Right? And there's less overlap, and overlap is the bad thing. You see, as you can see there, you get error because there's overlap. Look at that picture again. You have error because there's overlap in the distributions. So let's get rid of that. And the way we'll do that is realizing that sigma squared sub x bar, that's what we care about. It's not sigma squared, is it? It's sigma squared sub x bar. It's the sampling distribution of the mean, not the actual variance of the population, but the sampling distribution of the mean. We'll increase n. Right, look. Sigma squared sub x bar equals sigma squared over n. We have no control over those sigmas. They're population parameters. We have control over one thing. That. We have control over the n. N is the number of subjects. And take a look at this. How do we make sigma squared sub x bar bigger? Or sorry, smaller? We make n bigger. Because it's a fraction. It's being divided. It's a constant. This parameter is a constant. It doesn't move. And we're dividing by a variable, a thing we have control over. Yay! So we divide by n, we make n bigger. Now let's do a thought experiment. If we wanted to know if, oh, I don't know, who runs faster? Psychology students or biology students? What a bizarre experiment. I don't know what it would mean, and I don't know what the hypothesis was. So a lot of athletes in the psych. Most of the women's basketball team are in psychology, so we might have a shot there. Okay. We could randomly select some biology students, randomly select some psychology students, some biology students, and we run 100 meters and we detect the times and blah, blah, blah. We keep doing this and doing this and doing this. If we did it with 5 people, it's one thing. What if we had everybody, all psych students and all biology students? Then we'd know for sure. So when you go to the extreme of actually getting the whole population, you're going to know the answer. That's basically what this is saying, is that if we divide by a bigger number, so 5 students of each, then maybe 10, maybe 20, maybe 50. If we go up to, I don't know, say a couple hundred each, something like that, we would know the answer for sure if we got all the way to the top to the population as n approaches infinity. Yep.
In that case, why do we use just little n and not little n minus 1?
Because the math works that way. Because the central limit theorem tells us that the variance of the the variance of the sampling distribution, of the mean, is sigma squared sub n. It just is. There's a proof. Because this is for doing a population parameter. This is not a sample statistic. Right? So the sigma squared sub x bar is sigma squared over n. That's not a population, that's not a sample statistic, that's a population parameter that has, oddly, a sample statistic in it. Neat question. I've never been asked that. That's a very neat question. A really neat question. You're really thinking. That's cool. Other questions. Now you're all under all kinds of pressure because you can't probably top that. Okay. So we have control of this. We can make n bigger. The question is, do we want to actually have all the psych students and all the biology students run this race? Or would we be happy with, how many is just enough that we're really, really sure? Right? Because it costs money. We gotta somehow get all the psych students and all the biology students run 100 meters. It'd be nice if we knew exactly how many we needed. And that's what we're trying to figure out here. What the statistical power is what this is about. So, one thing we have to worry about is we got mu1 minus mu0. How big is the effect? If the effect exists, how big is it? And we want to standardize mu1 minus mu0. So we're going to use this as a hypothetical quantity. Note we can't know this because we don't know what mu1 and mu0 are, or mu1 and mu2 or whatever. So we have to make a lot of guesses here. Okay. So we're going to have a quantity called D. It's D for difference. And that equals mu1 minus mu0 over sigma. We're just going to standardize it by dividing by the standard deviation. So this population mean 1 minus population mean 0 divided by the standard deviation. Okay. All right. How do we know what those are? Because they're all we got population parameters galore. How are we going to guess what these are? Man, I don't know. Well, you could look at prior research, I guess, and take the average score that people get on some measure, and take the average standard deviation somehow, and we can make some guesses, some estimates. That seems really messy. It's also depending on other people. And I hate other people. That's not true. Like you guys. But my brother was on his way back from Cohen last night, and he texted me and said, "Why do people stand around to get onto airplanes, and their road hasn't been called yet?" And then I replied to him, "I hate the travel in public." And he said, "I'm at the point right now where I just effing hate everyone." I don't like depending on others. Even if they're good scientists, I don't want to depend on, oh, well, that's obviously what mu1 is, that's what mu0 is. Yeah, tied that back to this. Sometimes I wonder where I'm going, and then I go, okay. So the question is, how big is big enough? Like, look, there are differences there are sex differences, all kinds of them. How many of them matter at all is so vanishingly small. There are a couple that are very interesting. But I bet men have big toes on average than women, even correcting for body size. I'm making that up. But let's say that's true. Actually, that's probably true. Does it matter? Like, is that an interesting difference? Statistically, it may be significant. Is it practically significant? Like, is it a big enough difference? Like, if it's, let's say it's, I don't know, milligram difference in mass, would that make a difference in anything? No, we wouldn't care. If it was like a 10% difference or something, we'd probably go, oh, that's weird. Women have tiny little toes. Or men have giant gross toes. Could be either. Could be both. There's differences between groups all the time because everybody isn't exactly the same. That's how biology works, right? We aren't all the same. Doesn't matter unless you know you're got. I asked. There's a new person in biology, and when she was giving her job talk about something or other, I said they have to give them anti-rejection drugs. She goes, no, these mice are actually genetically engineered, so they don't reject organs. Oh, I see. So, because you're giving them things from the same, the same line. Okay. They're all the same. But the rest of us that aren't all the same from the same mom and dad and the same environment, we're all a bit different. So every group's a little bit different, right? But the differences are usually so small, we wonder how big is a difference that matters? So that's the question you have to ask. Does it matter, the difference? So how big is a big enough difference? Like let's say you look at, there's different sex classifications for the Olympics for athletics. Because women on average run slower than men. And it wouldn't be fair if you had a man category, everybody category, a woman would get a better chance, and it wouldn't be meaningful. So we say, but let's just say the difference was 0.01 seconds. Would we still have a women's 100 meters and a men's 100 meters? Well, no, because it's not practically significant, right? Doesn't matter. So it's that kind of thing. We have to wonder how big is big enough. Clearly, for running 100 meters, that's big enough. For other things, in the Olympics, shooting, like rifle shooting, pistol shooting, they actually don't have sex classifications. right? Do people just compete, mixed gender, mixed sex, whatever you call it? Because it doesn't matter how good a shooter you are based on chromosomes or whatever. It's not the way it works. Sex chromosomes. So, cool. The difference, if it's there, is so small it doesn't matter. It's decided a long time ago. Okay. So how big is a big enough difference? Well, Cohen had an idea. Cohen said, here it is. I'm going to look not at how big the difference is, because I can't know that for every possible difference between distributions, but I can look at the percentage of overlap. And then I can say how big that d value, mu1 minus mu0 over sigma, is for a given d. So I'll call a small difference. There's 85% overlap. Now think about that for a second. 85%. Is there an eraser? There is. I'm going to try to draw 85% overlap. That's about 85% overlap. That's a small difference. That to me doesn't matter. That's nothing. A medium one, which is 67% overlap, we're going to move that over now that's 2/3 overlap. That's still not very big. And a large effect, a so-called large effect, has 53% overlap. That's kind of like what we saw in the diagram that I had on the slide. You can see there's still a lot of error there, potential error. Huh. There's been a lot of, in the last few years especially, when people have been rethinking a lot of things about inferential statistics, a lot of people have been saying, a lot of people like a, quote, medium-sized effect, and then when you look at it on paper, you go, that's not medium, man. Cohen just chose these. I'll call these small, medium, and large. Like, yeah. Okay. So, it's entirely arbitrary, Cohen's method. It's entirely arbitrary. So, we combine this information with the effect of sample size, and we get what's called a delta statistic. Okay. Delta equals d and how it's a function, and the function of n. In other words, how n affects the statistic. So this can be used for any statistic. It's how the number of subjects affects the statistic you're interested in. So I'll go through this in just a sec. This isn't that difficult to do. The weird part about this isn't the arithmetic and the little bit of math we'll do today. It's thinking this way, because we have to think, oh, I know how big the effect is, and that's not something we can know. That's the hard part of this to me. Okay? So f of n is how it affects a given test. So for a t-test, f of n equals the square root of n. I know that looks like check mark n bar because that's what it is, but it's supposed to be square root of n. So I feel like the equation editor is a bitch. Like if you ever use an equation editor in almost any program, it's horrible. When you make one little mistake, the whole thing doesn't work. So I just did it that way. The other equations, you see, I did it properly, but I just didn't feel like it. I made these slides up 10 years ago. This stuff doesn't change. So that's the beauty of teaching stats. Like I don't have to keep current because this is current. Because this stuff really doesn't change. Also, it's fun. Okay. So, let's put this together. It's not so bad, don't be afraid. So if you know D, which you could never know, but you say, D, this is good, 0.5, yeah, we'll go with that, because Cohen said it was medium. And then you can, if you know D, you can figure out the sample size for a given power. Let's say we know D is 0.5, and that's what people, for the longest time, in fact, I believe the book suggests using 0.5 if you're doing power calculations. That's 67% overlap. They don't differ by much. Finding differences, by the way, with biological systems, which is what we're dealing with here, is hard. That's why it really bugs me people call chemistry and physics hard science. It's like this science, biology and psychology are hard sciences. They're harder to do. They're harder to do because we get these weird, stupid living things we're studying. Call it hard science and difficult science. I think it's a lot harder doing things with living beings. Oh, physics, it must be really hard. Oh, just do motion, the objects in motion stay in motion? Ooh. That must be really hard. Yeah, I always in physics grade 11. I was taking university physics. My knowledge of chemistry is gone. I was really good in high school, too. I got 103 in grade 13 chemistry. I got all the bonus marks on exams and stuff. I can't remember. I could probably still balance an equation. I could probably do that because that's like a puzzle. But the rest of the stuff is like, I don't know, atoms, all gone. Because I never used it again. I use neurochemistry, like biochemistry all the time, but it's like, anyway, who cares? Now that you know, I know literally nothing and I'm faking everything. So, you usually pick 0.5, but it's small, man. I mean, it's called a medium effect because Cohen called it medium. That's the only reason we think we use it. Yeah. Okay, let's say we want a power of 0.8. We want an 80% chance of if there's an effect, we can find it. Does that make sense? So we're picking a power, just the same way we would pick alpha. We're going to pick a power. We're going to say, I want an 80% chance to find something that's there. Nice. See, this is the beautiful thing. D is going to be this. Beta is going to, 1 minus beta is going to be this. Alpha is going to be this. So you actually are telling what everything's going to be. And you look it up in our case, in the appendix called power, or you look it up in a delta table. But in our book, there's an appendix called power. And then that happened again. I don't know why. So, all you're doing here is using another table. So we're going to say D equals 0.5. 1 minus beta, or power, is 0.8. And alpha is going to be 0.05. Because that's what we always use, stupid tradition. D is kind of stupid tradition. We use it 0.5. And 1 minus beta is going to be 0.8. Okay, this is the appendix from the book. It's a couple editions ago, but it's the same thing. So let's get rid of some of this stuff and zoom in here. So we have, should have done it like that. Let's go back for a sec. Right, there. Okay, so you see here, we have the alpha here, and there's 0.05 here in this column. Second column over from the left, and there's a value we're going to read out of it. The delta value we're actually going to read out of this. That's the key thing we're going to get. So let's back to doing these neat little effects. So we want 0.05, and then we're going to go down here till we get to 0.8. There it is. 0.8. And we recross to here, we get 2.8. Delta's 2.8. What are we doing? Don't worry. It all comes through in a second. There's going to be a formula we put this in, and it gives us an N. Okay. So N equals delta over D. Remember before I had the thing, and I said that D equals F and N, right? All I've done here is cross multiplied and made N not a square root, but I just squared it, right? So before I had square root of N times D equals delta, right? So I had this, I had delta, which is funny thing to write, equals d times the square root of n. I had that a couple slides ago. All I've done is I want to isolate the n. So I get delta over d equals the square root of n. I don't want the square root of n, I want n, so I get n equals delta over d squared. It's just arithmetic. I guess that's math-ish. So that wasn't magic. This is not a new formula. I just rearranged everything so I was solving for n. Yeah?
So the function turns into a square root?
It was a square root of n because the way that n affects a t-test, we're doing this with a t-test presumably, is that it's when you think about the standard deviation, it's standard deviation, not variance, so it's sigma divided by square root of n, right? If this was something else that was, let's say, something like analysis of variance, where you're working with variance, it wouldn't be square root of n, it would just be n. So now I take the d I knew, 0.5, the delta I looked up from the table, 2.8 over 0.5 and square it equals 31.36. I need 31.36 subjects in my experiment. If the difference is a 0.5 size and I want a 0.8 power, that's how many subjects I need. I'm sorry, participants. Experimental units. That's literally how simple this is. It's reading from a table and filling in. You get all values. So 32 people. If there's a difference, you'll find it. And every year, I have honor students, of course. Every year, I say, how many participants do you want to have in your experiment? And they'll say, well, as many as I can get. And I say, no. Remember that class just before the first test in 3256? What did I say? I said, do a power calculation. They go, oh, I can't remember how to do that. I say, yeah, but 30. You'll be fine. You don't need 80. Well, people will say, well, I got 6 groups and I want to have 40 subjects per group. Like, where are you finding all these people? You need about 10. You'll be fine. Now, if we increase the power, so let's make the power, you say, oh, all kinds of power. I want 99 power. I want Wayne Gretzky power. 0.99 instead of 0.8. I want to be 99% sure. Now the delta value in the table is 420. It's gone up to 420. Take my word, I looked it up. Suddenly now, to get a power of 0.99, to go up, now that is quite an increase. That's almost a 20% increase, 25% increase, right? 20, yeah, but a 25% increase. 19 and an 8, so it's almost 25%. But I've more than doubled the number of observations I have to take. If you think that's worth it, that's fine. I don't think it's worth it. I've always said to people, if you can't find an effect with 25, 30 observations, it's not interesting, probably. Clinically, there are different questions. But when I'm talking about, oh, does this somehow affect people's view, there's an experiment I'm going to run at some point about spoilers. And do they actually damage people's enjoyment of the media? Because I'm sick and tired of people telling me everything's a spoiler. So I'm going to run this experiment and how people's enjoyment of a story is. It's just a thing I'm going to do because I'm pissed off at people saying, it's a spoiler! Spoiler alert, we won World War II. Didn't know. Just tired. Sound good? That's what I'm going to do. If it doesn't show up with 25 people, then there's no effect. Because it's not a huge issue. If it's a clinical thing, it's different, okay? If we're talking about therapy outcomes or we're talking about some drug trial, different question. But when we're talking about regular mundane behavioral questions that a lot of psychologists, sometimes me included, do, I'm not curing cancer. You know what I'm saying? So if it's not there with like 30 people, yeah, oh, would it be there with 70? Great. So, it's my view. So what the hell is delta? It's a funny Greek letter. It's called the non-centrality parameter. We normally assume HO, right? We started by saying HO, and we have different shaded areas. Under HO, the expected value of T is 0. Think about that. Written up here. But X bar minus mu, if there's no effect, that should be 0, right? Right? But if we say that there is an effect, the expected value of T is going to be greater than 0. So how likely is T that we'll find a value of delta that is greater than T at 0.05? So all this is a T formula that does not equal 0. And then the thing is, you're going to say, David, it's never equal to 0. Yes, but the expected value, if there's no effect, is 0. If you have no effect, you did it a zillion times, you get 0. If you average, you don't have. So if there is an effect, it will be non-zero. So that's what delta is if you're interested. Like it's just that. It's how big. See to do this though, notice we had to know to do this. Do a power calculation. What do we have to know? We have to know D. And to know D, what do you need to know? Sigma square, or mu1 minus mu0 over sigma. Uh-oh, I have to know parameters. I can't know parameters. I have to know how big the effect is. Can I know that? Can I actually know that? No, I can't. It's unknowable. Can I make some guesses? Oh, I'll make some guesses and I'll say that 0.8 or 0.5 or maybe 1 is a big enough overlap for my interest, for my sake. But you know what? Can I actually know those values? No. Therefore, can I actually know the power of a statistical test? No, I can't. I can make a guess. A good guess, a good estimate. But it's still a guess and I can't really know it. It's all probabilistic. I can make statements that are probabilistic, but the difference here, when I say the probability of having a false positive of an alpha, probability of alpha, type 1 error. When I say I know that, I've set things up and I can tell you that's what it is. In this case, I actually can't know the power of a test. I can make some guesses, making a series of assumptions, including this is how big the effect is. And that's a damn big assumption, because I can't know that. And if I knew it already, I wouldn't have to do it science. Because it would be something I knew already. That's why this is really weird stuff to think about. It's valuable to know. And to do these things is important. When you're doing an experiment, and if you haven't done a power calculation beforehand, which you can do usually now using online calculators, or there are tables and books, a good statistics book, a good like graduate level, purely graduate level stats book will have power functions in the back of it. And it'll be like, how many between variables, how many within variables, blah, 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 blah. And then you just read off a graph how many observations you need per group. Or you can do, there's a lot of online calculators that are good. But if you just do a t-test, you can do this. This takes no time. It's easy. Please.
So you use that when you do the t-test?
That's the t-test. If this was with a z-test, no, z wouldn't be a good one. Z would work the same way, wouldn't it? Yeah, it would, because the variance of the sampling distribution of the mean is still affected by n, by root n. So we're exactly the same for a z. If you were doing an analysis of variance with two groups, which we aren't there yet, I think you all know what ANOVA is. We'll study ANOVA in the week from today. You would use n, not its root of n, because it's what variance, not standard deviation. Yeah. This would also work if you were doing correlations, because they're affected by root n. So if we're going to, how many subjects do I need to find a significant correlation? you would do like this. And again, that's the worst one. Significant correlation sometimes are like 0.2, which means literally nothing. Wait till we get the correlation on regression. Oh boy, I explained 4% of the data of the variance. Explained nothing, man. Other questions, good question. Other questions. This stuff is not easy to get your head around. The key takeaway, to me, is to do power calculations when you can, or at least, and if you can't, at least think about power. There's basically a law of diminishing returns when it comes to adding another set of observations. Every new participant you measure, every new observation you take costs you time, and everyone costs the same amount of extra time. But the amount of extra explanatory value you get is diminishing. Right? You get less and less power for each person or whenever you're studying, whenever you're observing that. So at some point, you got to say, I quit. And thinking that through is what gives you the nice balance between having good power, but also having not wasted your life collecting data. And then resources. I mean, collecting data costs money too. But you can't really know the power of the test, but you can guess it. Estimate is a better word. And you just have to know a few things. Any other questions? Like I said, this stuff's kind of hard to get your head around.